Hi guys,
Maisha, and I'm here with my team member.
I'm Dorothy.
Have you ever struggled trying to calculate thermodynamic properties using steam tables?
Do you struggle trying to find your thermodynamic properties like your entropy, enthalpy, internal energy? Always.
Or are you so unsure about what the state of your fluid will be given some conditions?
So what if all these can be done with just input of some basic two values you already know? Well, we are here for you. You all agree with me that in thermodynamics we often rely on steam tables and charts to find our properties like enthalpy, entropy, and specific volume. However, this process can be time consuming, prone to human error, and sometimes difficult to interpret. So, the aim of this project is to make all these very easy, instant, accurate, and also with graphical visualization, making it easier to draw your graphs. Interesting, right? Yes, come with me, let's dive into this project. This project focuses on the development of thermodynamic property calculator with a graphical user interface using Python. The aim is to provide a simple and efficient way to determine thermodynamic properties of pure substances by inputting any two independent variables. And also, you'll be able to draw your graphs with this project system. In creating this program, we use Python for our programming. We installed CoolProp library for our thermodynamic property calculations, tkinter for our graphical user interface, matplot library for plotting our graphs, and also NumPy for our numerical computation.
How our systems work. So the user begins by selecting a fluid and then choosing any two independent thermodynamic properties along with their corresponding units. After entering these values and clicking the calculate button, the system first converts all your inputs into standard SI units. It then uses the CoolProp function to compute various properties, including temperature, pressure, enthalpy, entropy, internal energy, specific volume, and specific heat capacities. These results are then displayed instantly within the interface. We are moving to the state determination. So, an important feature of our system is automatic state identification. The program calculates the vapor quality and then it uses that vapor quality to determine the state of your fluid. Depending on the value, the system identifies whether the fluid is compressed liquid, saturated liquid, a two-phase mixture, saturated vapor, superheated vapor, or in a supercritical state. This removes the need for manual interpretation and improves accuracy. So, if your quality, which is X, is less than 0, it's a compressed or a subcooled liquid. If it is equal to 0, it's a saturated liquid. If it is between 0 and 1, it's a two-phase mixture, that's a liquid and a vapor. If it is equal to 1, it's a saturated vapor. And if it is greater than 1, it's a superheated vapor. In addition to our numerical results, our system also generates key thermodynamic diagrams. This includes the TS diagram, PV diagram, TV diagram, and then the PT diagrams. To generate these graphs, the system computes your saturation properties over a temperature range between the triple point and then the critical point of the selected fluid. These values are then plotted to form the saturation dome, clearly showing phase boundaries and then the thermodynamic relationships. This makes the system not only computational but also highly visual and educational. So, our graphical user interface was designed to be simple and user-friendly. It allows users to easily input values, select any unit of their choice, compute results, and view graphical output in an organized layout. The interface was enhanced using TTK to provide a more modern and visually appealing design. In conclusion, this project successfully combines accurate thermodynamic calculations with an interactive interface and graphical visualization. It eliminates the need for manual table lookup, reduces errors, and improves understanding of thermodynamic processes. As a result, it serves as both a valuable learning tool and a practical application for engineering analysis. Let me take you through how our project worked practically. So let me take you through how our thermodynamic fluid properties calculator works. So first, we imported our libraries, which are NumPy, Warnings, Matplotlib, CoolProp, Widget, and stuff. So we use the try and accept so that if the input you give us is too low or too high, our our calculator won't crash. So it will just give you a value. Maybe it could give you not a number or yes something which is not right, but it won't crash our calculator. So let's run this and see. Yes, so our matplotlib is loaded and all our libraries are ready. So let's move to the second one. This is where we imported the CoolProp, and we use props si so that whichever unit you give us, it will just convert it to the standard units, and then it will calculate using the standard units. So the same way we also use the try and accept here too. And then let's run this one too. Okay, so these are the fluids we imported. We imported 150 fluids from CoolProp. Yes, so as you can see, there are many fluids. Yes, you can choose from any fluid, you can choose from this any fluid you want. And this is where the calculation itself is. So yes, so let me just run it for you to see. Yes, so our thermodynamic solver is fixed and is ready to do your calculations. So let's move to the unit conversions. Let me run this one too, so that you just see. Yeah. So our unit converter is also ready. So we move to the plotting function. This way it plots our graphs. Let me run this one too. Yes, our plotting function is ready. So that means we have no problem so far. Now let's move to the whole. Now let's move to the whole thing. This is where the graphical user interface shows, and then this is where all the calculations go. So let me run this for you to see how our calculator looks like. Yes. So this is how the calculator looks like. So first let's start. Yes, so it has already given us a setup. Let's just go with this one and see. So normal, let's go with 3.15. So these are so yes, we are going with the temperature, and then the units will be in Kelvin. Let's maintain that. And then the property, yes, so a second property, let's go for pressure. And then yes, let's leave it at 101.101325, and then the unit will be, let's leave it at Pascal. And then we want to see temperature, we want to see density, we want to see this. So let's tell it that we want it to show us our diagrams. So let's calculate. Yes, so it has told us that our fluid is water, and at that state it's a gas. So that means yes, it's a gas in this state. So let's show. I want to show you how the graphs look like. Yes, so these are the graphs. So these are our graphs. So this is the TS diagram. That's the temperature entropy graph of water at those at those conditions, and this is the temperature volume, this is our pressure volume, and then the last one is our pressure temperature diagram. So this is how our calculator works. So let me try giving. So what if we give it something so abstract that it can work? Let's see if it can. So that will show you that okay, yes, it won't crash. Our thermodynamic calculator will not crash. So let's start with maybe let's still maintain our temperature. Let me give it degrees Celsius. Yes, so that's, we all know that okay, so 100 degrees Celsius, and then The pressure is still this. And then let's give it 101.325. So here kilopascal. Let's see if it can convert to the standard units. So we are calculating again. Okay, yes, it has given us the same thing. And you see all our outputs are in SI units. That's why we are seeing 373 here, even though it's 100 here. So that's why we are seeing 373 here, even though it's 100. So it gives us it changes everything to SI units. So we are done. Let's see what the graphs looks like. Yes, you can see that they are all the same. We are still getting the same graph.
We hope you see it too. Thermodynamics can actually be this exciting. No more struggling with tables, no more guessing. It's all been made easy and intuitive. Thank you for watching.
Bye.